in my last class we discussed the use of pulse width modulation in inverter voltage control. So I will repeat, pulse width modulation in inverter output voltage control, okay, not inverter harmonics control, no. Pulse width modulation is used for inverter output voltage control, and if you switch the device in a particular fashion, harmonics can be eliminated, okay. So remember, if you switch the device in a particular fashion, you can eliminate certain harmonics. So if there are or if the number of pulses is an odd multiple of 3, then you have no subharmonics, no even harmonics, and there will be a 3-phase symmetry, okay. We also discussed about the sinusoidal PWM technique, wherein a sine wave of desired magnitude and a desired output frequency are compared with a high frequency triangular. The frequency of the sine wave or the modulating wave decides the frequency of the fundamental component of the output voltage, and magnitude of the sine wave decides the magnitude of the output voltage, okay. And we found that the harmonic spectrum has 2 side bands near the switching frequency or near the carrier frequency, okay, or near the frequency of the triangular wave. See, in the last class I did show you the expression, and we have taken the ratio to be 45, the ratio of the triangular wave to the ratio of sine wave, we took it as 45, and then the frequency of the predominant harmonic is 45 into the frequency of the sine wave plus or minus twice the frequency of the sine wave, okay. We found that as the modulation index increases or as m increases above 1, the inverter from pulse width modulation to transfers to the 6-step operation. I will repeat it, till modulation index is equal to 1, inverter is under pulse width modulation control. Above 1, it goes into a 6-step operation, okay, or a square wave mode. The moment it goes to square wave mode, harmonics reappear, okay. The frequency of the predominant harmonic in square wave is again the 5th and the 7th and so on, 6n plus or minus 1, okay. So using sinusoidal PWM technique, we could push the predominant harmonic to a high frequency till the rated frequency, but then we found that the utilization of the DC link or the input voltage source reduces, or the utilization becomes poor, okay, because the peak of the fundamental component of the line to line voltage, we found that it is VDC by 2 into root 3. So this is the peak of the fundamental component of the line to line voltage in a PWM inverter, okay, which is less compared to a square wave operation. That's the reason, in the sense, using PWM technique we eliminated the harmonics in the process the utilization comes down. Okay. I told you that instead of using a sine wave, we could use any other modulating wave having other waveform, but then the criteria is it should not affect the harmonic spectrum, or it should not deteriorate the harmonic spectrum, and you should try to improve the DC link utilization. Okay. So that is the reason we added a third harmonic component. See here, there is a fundamental component. It was just 1 sin omega t, okay, Vm sin omega t or is equal to 1 sin omega t, whereas in third harmonic injected PWM technique, see, we have increased the fundamental or magnitude of sinusoidal modulating wave by 15%. See, it is 1.15 sin omega t plus 0.19 sin 3 omega t. Okay. We added these two waveforms and we got a new modulating wave. So in this new modulating wave, there is no peak which appears in a sine wave. The area is improved here, okay. But then if you see the harmonic spectrum of the line to line voltage, there is no third harmonic, there is no third harmonic. What did we achieve by adding a third harmonic component to the modulating wave? We could improve the peak of the fundamental component, okay, that increases by 15%. How it improves by 15%? Because the peak of the sinusoidal modulating wave itself is been improved by 15%. Okay. So peak of the fundamental component is now 1.15 times root 3 VDC by 2, that is VDC itself. Okay. So this is about sinusoidal PWM technique and a third harmonic injected PWM technique. There is yet another PWM technique, what is known as the harmonic elimination technique. Okay. It says undesirable harmonics can be eliminated and the fundamental component can be controlled by creating notches at predetermined angles. I will repeat, see here. Undesirable harmonics can be eliminated and fundamental component can be controlled by creating notches at predetermined angles. Okay. Now we will see how to determine these angles. Okay. Before that I will explain to you this statement. What it says is, if there are n switchings per quarter cycle, remember n switchings per quarter cycle, n minus 1 harmonics can be eliminated and you can control the fundamental. I will repeat, if there are n number of switchings per quarter cycle, n minus 1 harmonics can be eliminated and the magnitude of the fundamental can be controlled. Okay. See, I will explain to you. See, this is a pole voltage waveform of a square wave inverter. See, I am creating 4 notches, I am switching at 4 different places at alpha 1, alpha 2, alpha 3 and alpha 4. See, pi by 2 is here per quarter cycle. Okay. Similarly, at pi minus alpha 4, pi minus alpha 3, pi minus alpha 2, pi minus alpha 1. Okay. Condition here is alpha 1 is less than alpha 2, less than alpha 3, which is less than alpha 4, which is less than pi by 2. Okay. So there are 4 switchings per quarter cycle. So you can eliminate 3 harmonics and you can control the fundamental. Okay. Now which 3 harmonics that you want to eliminate? See, VA0 has a quarter wave symmetry, okay, and an odd function. What is the Fourier series of this square waveform of VA0? It's an odd function. So average value is 0. All cos n omega t terms are 0. Like Fourier series is given by A0 plus sigma a n cos n omega t plus b n sin n omega t. So it is an odd function, so all a n cos n omega t terms are 0. Okay. So I need to know, or I need to calculate what are the various odd harmonic components that are present in this waveform. Okay. See, the expression for the coefficient of the fundamental and the harmonic component, okay, given by this equation. Okay. I have just written this equation. You need to determine, this obtained by determining the harmonic or writing the Fourier series of the waveform and determining various components. It's as simple as that. Okay. Okay. So it is given by Bn is equal to this equation. Okay. Now using this equation, I will show you how you can eliminate the harmonics. Okay. Now assume that there are 5 switchings per quarter cycle. Okay. 4 harmonics can be eliminated. Now what are the 4 harmonics? System is a 3-phase 3-wire system. So you can conveniently neglect triplet harmonics. No even harmonics are present. So therefore the harmonics that are to be eliminated are 5th, 7th, 11th, 13th. Okay. See, now using that equation which I showed you just now, I will write this equation. See here, B1 is equal to 4 by pi to 1 minus 2 cos alpha 1 plus 2 cos alpha 2 minus 2 cos alpha 3 plus 2 cos alpha 4 minus 2 cos alpha 5. 1 to 5, because there are 5 switchings per quarter cycle. See here, 1 to m, there are so many switchings per quarter cycle. Okay. This is for fundamental B1 4 by pi and cos whatever alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. Okay. Now which is the harmonics to be eliminated? 5. Okay. The 5th one. So B5 is equal to 4 by 5 pi, okay, and wherever alpha comes you put 5 alpha. Okay. So in this equation you substitute alpha 1, substitution 5 alpha 1 to alpha 1 and same equation, and here B5 4 by 5 pi. See, here is the equation, B5 is equal to 4 by 5 pi and same thing, same equation. So this has to be eliminated. I will equate it to 0. What is the next harmonic? It is the 7th harmonic. See here, I will write the same equation. I will substitute 7 for n, 4 by 7 pi, and wherever there is 5 I will write 7. Okay. Again I have to eliminate it, I have to, or I will equate it to 0. The next one being the 11th one. See here, n is equal to 11 now. 4 by 11 pi, again cos 11 alpha 1, 11 alpha 2, so on, same is equal to, again equal to 0. And the last one is the 13th, 4 by 13 and same thing to 0. Okay. So I have 5 non-linear transcendental equations that have to be solved. How do I solve this? Okay. There are 5 equations, 5 variables. Okay. So definitely I need to use some numerical technique to solve them. Okay. Now how do you choose the value of the fundamental? Because all 4 equations have been equated to 0, because those harmonics should be eliminated and fundamental should be controlled. Now how do you know, or what should be the value of the fundamental? The fundamental component is the system requirement. It depends on a V by F curve. It's a V by F curve. Suppose the frequency of the fundamental is, say, if I know the V by F curve and if I know the frequency of operation, I can get the magnitude of the fundamental that is required. Okay. See, I will repeat. If the V by F curve is known, okay, depending upon the frequency of the fundamental, I can get the frequency of the fundamental. That is nothing but B1. Okay. So you need to know the value of the fundamental that you want at a particular frequency. Okay. So I equated from a V by F curve to be B1 to be equal to 0.986 per unit. Okay. And I got these values for alpha. See here, alpha 1 is 10.514 degrees. See here, I get 23.228 degrees, again 29.289 degrees, alpha 4 is equal to 46.421 degrees, and alpha 5 is equal to 50.157 degrees. So if you switch at these angles, these particular angles, you can eliminate 5th, 7th, 11th, 13th, and you can control the fundamental, and its magnitude is found to be 0.986 per unit. Okay. So that's about the harmonic elimination technique. What are the disadvantages of harmonic elimination technique? Disadvantages are very obvious. See, as the number of switchings increases, okay, you will have a larger number of equations that you need to solve them. Okay. Say if there are, say, 15 switchings per quarter cycle, okay, so you will have 15 equations or nonlinear transcendental equation that you need to solve them. Okay. Now of course this could not be a disadvantage now, because powerful numerical techniques are available, powerful computers are also available. The second disadvantage is, see the angles that you are getting, alpha 10.514 degrees, 23.228 degrees. See, I will request you to do this exercise. You approximate these angles, say 10.5, here 23.2, 29.3 and 46.4 and 50.2. Okay. You approximate these angles and substitute in those equations, you will find that there is a significant increase in the harmonics. Okay. See, only when you switch at these angles you can make 5th, 7th, 11th, 13th, 0. If I approximate it, okay, there is going to be a significant rise in the harmonics which are already eliminated. In fact, they will not get eliminated. Okay. See, after all, we need to implement it in real time, in the sense you have to implement it, for an inverter. Okay. So you need to use a powerful processor or an intelligent controller. Okay. So while implementing these angles, there is for any processor there is a maximum value of accuracy. Now below or above that you cannot achieve it. Okay. So resolution is always there, in the sense at what value of what is the lowest value of theta that you can implement it. I don't think you can go in or you can implement it to a value to a third decimal value. Maybe it's going to be extremely difficult. So if I am approximating it to a first decimal, there is going to be a significant increase in the harmonics that are already eliminated. And in this harmonic elimination technique, what happens is you might have eliminated 4 harmonics, or till the 13th, the next immediate dominant harmonic, that is 17th, it really gets amplified. Okay. So if you determine the magnitude of the 17th harmonic, because till 11 you have eliminated, the next immediate it is 17th, you may get a value which is equal to the value of the fundamental itself. I will repeat. See, value of B1 we found to be 0.986 per unit. Now using these angles, okay, without approximating it, if you try to find or try to calculate the 17th harmonic, you will find that the magnitude of the 17th harmonics, which is maybe equal to or maybe slightly higher than 0.986 per unit itself. Okay, it really gets amplified. Okay. But then again, the frequency of the 17th harmonic may be higher, and it gets filtered out by the machine inductance. That whatever that I have told in my last lecture holds good. But this is the disadvantage of harmonic elimination technique. It's quite attractive because you can try to optimize certain performance index of a machine. Okay. So what the harmonic elimination says? You need to switch at predetermined values, or in other words, if there are n number of switchings per quarter cycle, n minus 1 harmonics can be eliminated and the fundamental can be controlled. Okay. So that's about sinusoidal PWM technique and the harmonic elimination technique. So if you make certain observations on whatever that you have studied so far, I can sum up them to the first one. There should not be, or there should no pulses of opposite polarity in the half cycle of line to line voltage waveform. Okay. A well designed PWM strategy should have these features. One is, there should not be a pulse of opposite polarity. See here, supposed to be only positive to 0 and positive transition. This is the first half cycle of the line to line voltage. Same thing should repeat in the negative half. But then here you may have a pulse of negative polarity. You may find in sinusoidal PWM technique. Okay. Now, what happens if this sort of a pulse is there in the voltage waveform? You will have a large ripple current. Ripple current increases. Okay. Second one is, there should not be subharmonics. Subharmonics should be 0. Subharmonics are those harmonics whose frequency is not an integral multiple of the fundamental component. Okay. The frequency of the subharmonics is not an integral multiple of the frequency of the fundamental. So, subharmonics should be 0. They will be 0 only when the PWM waveform is in synchronism with its own fundamental. Okay. See here, PWM waveform must be synchronized with its own fundamental. Okay. Oh, in other words, pulse number should be an integer. This I already told you in my last lecture. Okay. In addition, there should be a half wave, a quarter wave, and a 3-phase symmetry. Okay. These are all desirable. Okay. Also, one should not allow different phases to switch simultaneously. I mean, see, when S1 is switching, you should not allow S3 or a complement of S3 in B phase, and in C phase S5 and complementary of S5, you should not switch, or at a time only one switch should change its conducting state. I will repeat, it is always desirable to have one switch changing its conducting state. So, you can determine the frequency of the ripple of the current very accurately. Okay. But then, so far we observed that you can independently control one leg of the VSI. In other words, a 3-phase PWM inverter can be thought of as a 3 separate driver stages, 3 separate legs of a driver. Okay. Each creates phase waveform independently. Okay. See, I will repeat, read this. A PWM inverter can be thought of as 3 separate driver stages, in the sense there are 3 independent legs. I can control them independently. Okay. And they create the phase waveform independently. Okay. While controlling phase A, we do not bother about what happens in phase B and what happens in phase C. Okay. That is what we did in sinusoidal PWM technique. We took a sine wave compared with the triangle. Okay. It may so happen that phase A, upper phase A device may be switching along with phase B and along with phase C. Okay. So, at any given instant, either 1 or 2 or all 3 switches may be either turned on or off. Okay. So, one of the features that I told you here is, do not allow phases to switch simultaneously. Okay. Whereas, in the sinusoidal PWM technique, you cannot ensure this. There is a PWM technique, what is known as the space vector PWM technique. I will repeat, space vector PWM technique, which does or which achieves all the above features. Okay. The space vector PWM technique. That is the reason it is very popular. It is very popular. okay, and it's very simple to implement also. I'll explain to you how to implement a space vector PWM technique. So if you see the modern digital signal processors, DSPs, okay, there are dedicated pins in the DSP which give a pulse width modulated waveform using space vector modulation. See, from this you can conclude as to how popular this space vector PWM technique is. There are DSPs, say, okay, digital signal processors, wherein they have dedicated pins wherein you can get a pulse width modulation waveform using space vector PWM technique. It's very popular and very simple to implement also. Okay, so before explaining what is space vector modulation, I'll explain to you what is space vector. Okay, so let say I'll take 3 phase waveforms, that is VAN is equal to Vm sin omega t, Vb is equal to Vm sin omega t minus 120 degrees, and Vc is equal to Vm sin omega t plus 120 degrees. Okay, I have 3 vectors which are displaced by 120 degrees. So at any given time, the instantaneous value Va plus Vb plus Vc is equal to 0. So I can represent these 3 vectors by one vector, okay, what is known as the space vector. This vector I can represent it in 2-dimensional space. So it has a x-axis component and it has a y-axis component. Okay, so I'll repeat. 3 phase vectors Va, Vb, Vc, or I can have currents also, 3 phase current, not a problem. Okay, so you can represent it by what is known as one vector. So it has a x-axis component and a y-axis component. Okay, so here the space vector is defined as Vs is a space vector is Va plus Vb into e to the power j 2 pi by 3 plus Vc into e to the power j minus 2 pi by 3. See, this is the definition of the space vector. Okay. Now I'll substitute for Va, Vb and Vc and I'll simplify. Okay, I get this equation. So what is this equation? It says that space vector is a vector having constant magnitude of 3 by 2 times Vm. Okay, it has a constant vector of 3 by 2 times Vm. Okay, and it rotates in space at omega radians per second. Okay, has a magnitude of 3 by 2 Vm and rotate in space at omega is equal to at omega radians per second. What is this omega? Omega is the frequency of the sine waves itself, 3 sine waves, sine omega t. Okay, so in space I can represent it by this. The locus is a circular because I have assumed all 3 to be sinusoids. Okay, all 3 to be sinusoids. So Vs rotates in a circular locus, magnitude is 3 by 2 times Vm, omega is same as the omega is this omega is same as the omega of those Va, Vb and Vc. Okay, this is something similar to maybe rotating magnetic field in induction machine, CV. Okay, that also rotates at 3 by 2 times the magnitude of this one and at omega. So this is space vector. Now I said space vector can be represented or it can represent it in 2-dimensional space. Okay, see here I have A, B and C, angle between them is 120 degrees. At any given time they are in this fashion, maybe A, B, C may be continuously rotating, no problem. So I will represent it in a 2-dimensional space, x axis component and a y axis component. Sometimes it is known as a d axis component and a q axis component, direct axis and a quadrature axis, or you can also say that x axis and y axis, does not matter. And this is the space vector Vs. How do you determine the x axis component and the y axis component, or how do I represent these 3 vectors in 2-dimensional space? It is very easy. I need to just resolve them along x axis and y axis. It is as simple as that. Please do not get confused. It is, I have to just resolve them along x axis and y axis. What is sigma Vx? What is sigma Vx, or what is the sum of all the x axis components of these 3 vectors? Va itself, x axis component of A phase is Va itself, okay. B phase is Vb into cos 120, this is 120, cos 120 is minus half, okay, and Vc is, x axis component of Vc is Vc into cos 240, that is again minus half, okay. So Vx is Va, okay, minus half of Vb minus half of Vc, that is sigma Vx. So if they are balanced, so I have Vx is equal to 3/2 times Va itself, because this is Vb plus Vc is nothing but minus Va. Okay. And what is Vy? The y axis component. Y axis component of A phase is 0, B phase is sin 120, that is root 3/2, and C phase is sin 240, that is minus root 3/2. So I will take Vy is equal to root 3/2 Vb minus Vc. So if I know the value of Va, Vb, Vc, I can determine Vx and Vy, and therefore Vs, okay. So to determine the space vector, I need to know Van, Vbn and Vcn. I have a 3-phase inverter, okay. So assume that it is feeding a star connected load. How do I determine Van, Vbn, Vcn? See, I had drawn the phase voltage waveform for a star connected load in 180 degree conduction, inverter with 180 degree conduction. We found that the magnitude is 1/3 and 2/3, a 6-step waveform that we got. I had used an equivalent circuit approach there. So I took 6 cases or 6 possible conduction states of the inverter, and for each case I determined what is Van, what is Vbn and what is Vcn. Please recall, I said if upper switch is on, that point gets connected to A phase, and when the lower switch is on, that phase connected to, when the upper switch is on, it gets connected to the positive DC link. When the lower switch is on, it gets connected to the negative DC link, okay. And the potential of point A, point B, point C with respect to the center point of the DC link is known if the conducting state of the switches are known. Here I will derive a very generalized expression, okay, and you will find that this is bit simpler Okay, we can determine, or we'll write it in a matrix form, a very simple matrix. Okay. So consider an inverter feeding a star connected load. Okay, again I am taking center point of the DC link as a reference point. Okay, so when the device, upper device is on, potential of ABC could be or is VDC by 2, and if the lower switch is on, it is minus VDC by 2. So now I can write VA0 or VAO is equal to VAN plus VNO. Okay. Similarly, VBO is equal to VBN plus VNO. Similarly, for VCO equations. So I have 3 equations here. I will add these 3 equations. Okay. When I add them, I will find that VIN plus VBN plus VCN becomes 0. Okay. So therefore, 3VNO is equal to VA0 plus VB0 plus VC0. Okay. So therefore, VNO is equal to 1/3 of this equation. Now I will substitute for VNO. So therefore, I can get VIN in terms of VA0, VB0 and VC0. See, when the inverter is switching, I know, or potential of A, B, C with respect to O are known. Okay. So now I found an expression for VNO in terms of VA0, VB0 and VC0. So I substitute this value in these equations, okay, and I can get expression for VIN, VBN and VCN in terms of VA0, VB0 and VC0. See, if you substitute this equation in first, I will get this 2/3 VA0 minus 1/3 of VB0 plus VC0. Similarly, VBN is equal to same thing, is B is here, so 2/3 VB0 minus, now since B is here, B should not be here. See here, A is here, there is no A here. Similarly, CN 2/3 VC0 and no C here. Coefficients are same. So if I write in matrix form, see VIN, VBN, VCN, so 1/3 I will take it out. I have a very simple matrix, very easy to remember. 2 minus 1 minus 1, minus 1 2 minus 1, minus 1 minus 1 2. VA0, VB0, VC0. See, all the diagonal elements are 2, okay, and remaining elements are minus 1, okay, multiplied by 1/3. So I can determine VIN, VBN, VCN by knowing VA0, VB0 and VC0. So VA0, VB0, VC0 are known if the conducting state of the switches are known. Okay. So now you do not need to determine, or you do not need to use the equivalent circuit approach, or the approach which you used while drawing the phase voltage waveform in a 180-degree conduction inverter. Okay. But then if you use this approach, you will get the same result. Okay. I had told you this. We have 3 switches in the upper 3 amps. Okay, they could be either on or off. So there are 8 possible states of the inverter. What are the 8 possible states? They are 0, 0, 0. In other words, all 3 switches are off to all 3 switches are on. I am just monitoring the upper switches, that is 1, 3, 5 or SA, SB, SC. Okay. Now what happens when all 3 are on or all 3 are off? When all 3 are off, or when upper 3 switches are off, lower 3 switches are on. Therefore, point A, point B and point C, they are connected to negative DC bus. Okay. So if you substitute these values here, you will find that VIN, VBN, VCN, they are equal to 0. All 3 are zeros, okay, which is obvious also. All 3 points are connected at the same potential. Okay. Sorry, all 3 points are connected to the same point. Okay. So VIN is 0, VBN is equal to 0, VCN is 0. Therefore, x-axis component or sigma x-axis component of all 3 phases, that is nothing but Vx, that is also 0. Also the Vy, the sigma y axis component of these vectors, is also 0. So therefore, the space vector magnitude is 0, angle tan inverse y by x is also 0. Okay. So we are at the origin. So when all upper 3 switches are on, that is 1, 1, 1, and when all the upper 3 switches are off, that is 0, 0, 0, the space vector, magnitude of the space vector is 0, okay, and angle is also 0. So in the xy plane, you are at the origin. Now what happens when A phase, upper switch of the phase A is on and remaining 2 switches are off? Okay, that is S1 is on, S3 and S5 are off, that is S6 and S2 are on. Since A phase is on, it is Vs0 is Vdc by 2, Vb0 and Vc0 are minus Vdc by 2. Okay. Now I will substitute these values in that matrix and will get this value. So Vin is equal to 2 by 3 into Vs0, that is Vdc by 2, plus this. So it is equal to 2 by 3 Vdc. See, in this matrix, I will repeat, you just substitute for Vb0 and Vc0. Vb0 and Vc0 both are equal to minus Vdc by 2. So this becomes plus. Okay. So Vin is 2 by 3 Vdc, Vbn and Vcn are minus 1/3 Vdc. See, same result we got in that the procedure that we used to plot that 6-step waveform, phase to neutral. When one of the switches is on, okay, one of the upper switches is on, only one switch is on in the upper half, at that time the phase voltage of that phase is 2 by 3 Vdc, and the phase voltage of remaining two phases is minus 1/3 VDC, remember. Okay. We are here also we are getting the same thing. So what is Vx or the sigma x axis component of VAN, VBN, VCN? Vx is nothing but 3/2 times VAN, this is the expression that we have derived, okay, that is equal to VDC itself. See here, okay, Vx is 3/2 times VA and Vy is square root of 3/2 times VB minus VC. Okay. So what is the y-axis component? VBN and VCN are same, minus 1/3 VDC, therefore Vy you will get it as 0. So what is the space vector? Magnitude of space vector is VDC itself, because y is 0, square root of Vx square plus Vy square, and angle is 0. Okay. Tan inverse y by x, y is 0. Okay. So VDC by 2. So therefore for 0, 0, 1, I have a space vector which is equal to VDC at an angle 0. So I can straight away write for 1, 1, 0, okay, the magnitude of the space vector is VDC at an angle pi radians. Okay. So for 0, 0, 1, it is VDC at angle 0. So therefore for 1, 1, 0, which is a complementary of this, my vector is also at 180 degree to the previous position. So VDC at an angle pi. Okay. If you are not convinced, you just work out, you will get this answer. Okay. More about the space vector PWM technique I will cover in the next class. Thank you.